And how can we now explain the stability and reactivity of aromatic and anti-aromatic compounds? Therefore, we should draw the molecular orbital diagrams, and more specifically the so-called frost circle. So let's start with the frost circle of benzene. If we want to understand the reactivity and stability of benzene, we will start with drawing the hexagon, which is the overall structure of the benzene molecule. And we have to draw it in that way that one of the vertex points down. So like this. Afterwards, we draw a circle around the hexagon, and each intersection between the circle and the hexagon represents then a molecular orbital. As we have the energy scale in the vertical direction, we directly have the correct energy positions of these molecular orbitals if we just follow these intersections. Accordingly, we just draw horizontal lines from these intersections towards new energy diagram. And you can see here we have these dotted lines which represent the relative energy of the corresponding molecular orbitals of each intersection here. Afterwards, we need to draw horizontal lines through the midpoint of the hexagon, and all molecular orbitals which are below this horizontal line are the bonding orbitals, whereas the molecular orbitals above this horizontal line are the anti-bonding molecular orbitals. And finally, we need to fill all molecular orbitals, and we know that we have 6 pi electrons. That means we start filling from bottom all molecular orbitals, and each molecular orbital can get 2 electrons as long as they are paired in the opposite direction. So then we can see that after filling, we end up with 3 filled bonding molecular orbitals and only empty antibonding molecular orbitals. And at the end, this drawing here represents the molecular orbital scheme for the pi system of this 6-membered framework. And we can explain the special stability of benzene based on this scheme here. So as we only have filled bonding molecular orbitals, but no filled or also not half-filled antibonding molecular orbitals, benzene is very stable. Furthermore, the frost circle can also be used to determine the number and relative energies of molecular orbitals of other planar cyclic compounds. So, for example, we can have a look on the frost circle of cyclobutadiene, which has a square shape. And therefore, we start quite similar as we did for benzene, but this time we do not draw a hexagon, but a square. And again, it is important that one vertex of the square points down. Afterwards, we draw a circle around the square, and again, each intersection between the circle and the square constitutes then one molecular orbital. Subsequently, we draw again a vertical line through the midpoint of this hexagon, and then we see that this time we have 2 molecular orbitals exactly on this line which goes through the midpoint. And this kind of molecular orbital is called non-bonding orbital. Afterwards, we fill up the molecular orbitals with electrons, and this time we have 4 pi electrons. That means we end up with 1 filled bonding molecular orbital and then 2 half-filled non-bonding orbitals, while the antibonding molecular orbital is empty. And the fact that we now have 1 filled bonding molecular orbital and 2 half-filled non-bonding orbitals explains why an anti-aromatic compound is very reactive and unstable. And as you can see, we have 2 half-filled orbitals. That means we have 2 unpaired electrons. And it is energetically more favored if we do not have unpaired electrons in molecular orbitals. Hence, this molecule wants to change the situation with these unpaired electrons, and therefore it will react very fast in order to pair those unpaired electrons. And in this way, we can also explain why anti-aromatic compounds in general are more active. And to revise shortly, if we have an anti-aromatic compound, the compound is cyclic, planar, so we only have sp2 hybridized carbon atoms, and has an uninterrupted ring of pi electrons, whereby the total number of pi electrons is 4 times n. Conversely, an aromatic compound is cyclic, planar, has an uninterrupted ring of pi electrons, but the total number of pi electrons is 4 times n plus 2. And correlated to this lecture, you can do the worked example 22.1 and also the end of chapter question 1 of chapter 22. And then you should already read chapter 22.2 until next lecture.